Okay, guys, welcome back. Let us continue. First of all, is any questions anyone has at this point? We are jumping ahead. You're going to see here that these chapters are going to go pretty quick. I'm going to start with chapter 12. That in itself is a fairly short chapter, but it has a very important concept that we're going to utilize for the next chapter, chapter 13. Okay, well, if there are not any questions, let me proceed. Okay, now here we go. This is called the mole. Now, AKA mole. No, just the mole. There's a lot of confusion that happens here when you first introduce this concept, but I want you to think of it as what we call the chemist dozen, because the term dozen we're all familiar with. We're all familiar with what number a dozen has. So a dozen donuts, we have 12 donuts, right? Acres dozen, obviously we've got 13, but it's a number. It is a represents a number. It just happens to represent a humongous number. 6.02 times 10 to the 23rd. So here we go again with scientific notation. Remember, we used that a few chapters back. Refresh your memory on how to use the scientific notation in your calculator. Okay, now these numbers are pretty big. Now, this dozen was created, or this concept was brought to us by Avogadro. There's a picture of him in the bottom right corner, and an interesting character. It's a very, very large number. It has a symbol, a capital N with superscript A, which represents Avogadro's number. And just like a dozen represents 12, one mole represents 6.02 times 10 to the 23rd. If you move that decimal point over from 6.02 over 23 times, it gives you an idea how big that number is. It is humongous. Here's an example. Basically, that number is 602 sextillion. Humongous, right? It would take that number of years. You see that number? It would take 19 quadrillion years to count that number if you were to count one number or one particle per second. 1, 2, 3, 4. I'll see you in 19 quadrillion years. That gives you an idea of how big it is. There are some other numbers that give you a reference point. 21 zeros per sextillion compared to a billion. A billion has 9 zeros. Okay, quadrillion has 15 zeros, so on and so forth, and all the way down to the bottom. Yeah, you can imagine how many zeros you have. They even have numbers for something that has 100 zeros. All right, so 19 quadrillion years to count that number. That's a lot of particles, for one mole. And keeping that number in mind, we're going to be talking about a mole volume. So that gives you an idea when we talk about molecules of water, how many molecules of water we have. And they, for example, water has what we call an atomic mass. We'll get into that in a second, of 18 grams per mole. What that means is that if I weigh out 18 grams of water, I have 602 sextillion molecules of water, 6.02 times 10 to the 23rd. Okay, that's a lot of molecules for just 18 grams of water. And imagine the amount of water we have on Earth. A lot of molecules out there. A lot of molecules. So very, very, it's a small amount. But if we were to kind of give you some reference point, if you had 1 mole of softball, and we all know the size of softball, obviously a little bigger than a baseball. Okay, 1 mole of softballs would equal the size of the Earth. That's how many softballs we would have. It just gives you a perspective on how tiny these atoms are. Okay, so when we go to the periodic table, underneath the symbol, you saw an atomic weight. There's a number, a decimal number. If you recall, when we talked about this, that was the average weight, atomic weight of all the isotopes for that particular element. And every element, every isotope had a whole number. So we ended up taking the average based on the abundance of which isotope was more abundant, and it gave us we average them out, take into account the abundance of each one, and we end up with a atomic weight. So that number underneath the symbol on the periodic table is called the atomic weight. Carbon, for example, the average atomic weight for all the isotopes of carbon are 12.01 grams. Okay, now the units for the atomic weight are, let me write this down, are grams per mole. All of the atomic weights on the periodic table. Guess what? We got a ratio here again. Remember the ratio thing we've been dealing with, we work with? Because we can write this now with moles over grams. Okay, some number here, X. It depends on what the element is and so forth. So we can write it either as grams over moles or moles over grams. Okay, with that being the case, remember we talked about setting up your reaction or your calculations with conversion factors and keeping track of your units, because we're going to be using the atomic weights, the grams over moles, to help us to go from moles to grams and grams to moles. And which one we use depends on the problem and the units that we're looking for. Normally, if we're looking for moles, then we're using this one, right? Because moles is the numerator. If we're looking for grams, then we're using this grams over moles, because we want grams in the numerator, because the moles will cancel here, grams will cancel here, depending on what we multiply. Just like we did with the conversion factors back in the early chapters, okay? And I said, get used to using them in this manner, because they're gonna come in handy, because we will be able to set up at least 3 conversion factors, and you will get from apples to oranges, if you will, okay? Apples to oranges, because to get to apples to oranges as an analogy, not literally, but as an analogy, to get from moles of grams of carbon to grams of oxygen, they look very dissimilar, right? But we can get to it depending on the reaction, but we only can get through it through moles, because the one common factor that these calculations will have will be moles. So it looks like I got bananas and oranges, carbon and oxygen, grams of carbon. I want to get through grams of oxygen. In order to get through there, I got to go through moles, okay? Because that's the common factor that those two have with each other. And we also utilize the stoichiometric relationship between the ratio and reactants. Remember, we've been dealing with balancing the chemical reactions, because balancing the chemical gives us a coefficient that we're going to utilize, and we set that problem up in the conversion factor. Okay, so it's all coming, hopefully coming together here. Yeah. So on that periodic table, 1 mole of carbon atoms. If I were to weigh out 6.02 times 10 to the 23rd atoms of carbon, it would have a total weight of 12.01 grams. For sodium, if I were to measure out 6.02 times 10 to the 23rd sodium atoms, guess what? It's going to weigh out 22.99 grams. Okay. Think of it as eggs, a dozen eggs. Okay, think about this. You got 1 dozen. Because this concept too is sometimes is a little bit challenging. But think of it in terms of eggs, because we know that 1 dozen small eggs. Okay, maybe let's say 100 grams. Let's say 100 grams just for argument's sake. Okay, 1 dozen medium eggs, just for argument's sake, it weighs 200 grams. That obviously they probably weigh more than that, right? But just giving you some numbers here. And 1 dozen large eggs, yeah, they're bigger. They're going to weigh, 300 grams, for example. What is it that they all have in common? 12, right? Because dozen. And so down here, 1 mole of carbon, what they have in common is 6.02 times 10 to the 23rd atoms of carbon. Okay. 1 mole of sodium, 6.02 times 10 to the 23rd atoms of sodium. Now, carbon, when you look at carbon and compare it to sodium, okay, carbon is number 6, sodium is number 11, okay, on the periodic table. Obviously, sodium has more protons and some more neutrons, so it's going to weigh more, right? Just like 1 dozen small eggs is going to weigh less than 1 dozen large eggs. It's just more material, more matter for a dozen eggs, right? They're all eggs, but they're larger. So that's what we're talking about here with respect to the mole, because I can talk about the dozen and people get that very well. But then I throw in the term mole and it just throws you for a loop. But don't let that happen, because think of the dozen as think of the mole as the chemist does. It just happens to be a number much, much greater than 12. All right. All right. So when we talk about 1 mole of anything, no matter what it is, 1 mole of students, 1 mole of bananas, 1 mole of apples, 1 mole of atoms, 1 mole of ions or molecules or formula units, and sodium chloride, aluminum oxide, so on and so forth. It is 6.02 times 10 to the 23rd. It'll be no different if I said, give me a dozen atoms of silver, a dozen ions of potassium ion, a dozen molecules of water, a dozen formula units of sodium chloride. Okay, same thing. It just happens to be a bigger number, because that's what we're dealing with. These atoms are so tiny, it gives you a perspective as to how small these atoms are. All right, so how many grams, the question may be asked, using the periodic table, how many grams is there in 1 mole of carbon? Well, we simply go to the periodic table, find carbon, find its atomic weight, and guess what? It has an atomic weight of 12.01 grams. Okay, that's how much 1 mole of carbon weighs. 1 mole of gold, 196.797 grams. Sodium, same scenario, 22.99 grams. Okay, all of these have the number 6.02 times 10 to the 23rd. And if we go to the periodic table, we can arbitrarily pick any element. Okay, let me zoom it up a little bit. And if we look at, let's see, calcium. Okay, 1 mole of calcium would weigh 40.02. Oh, excuse me, 40.08 grams. All right. Cesium, CE, 140.12 grams per 1 mole. 6.02 times 10 to the 23rd. Okay. Anyone? Number 31 here, 69.72 grams in 1 mole. Boron has 10.81 grams in 1 mole. Okay, and so that number, that atomic weight, represents the weight for 1 mole of any of these atoms. Now, right now, we're talking about the atoms themselves, okay? Just the atoms. But let me go back to when we talk about the molar weight or the molar mass of, say, water, what do? All right, well, let's do this. It's going to come later, but I'm going to introduce you to it right now. H2O, okay? Well, we need to know the formula for H2O. And this is where we get to, remember, we've been writing formulas for compounds, putting them together to write formulas. Okay, so whether it be ionic compounds or covalent compounds, we've been practicing how to put formulas together. Once we have that information, then we go and figure out, we want the molar mass, called molar mass, or the molar mass of H2O, water. So we have oxygen. Oxygen, we look in the table, is 16 grams per mole. Okay. We have hydrogen. Hydrogen is 1.01, but we got two of them, so we got 2.02 grams per mole. Okay. That means that water has a total atomic weight or total molar mass of 18.02 grams per mole. Okay. And so again, like I said earlier, if I weigh out 18.0 grams of water, I have 1 mole. That means I have 6.02 times 10 to the 23rd molecules of water. Okay. And think about all the water on the earth. Heck, just think about the water in your body. Okay. That's a lot of water. That's a lot of molecules out just on the earth. Yeah. Tremendous number. Tremendous number. Okay. Now, let's go, and this is what the molar mass is all about. So what they're asking you here is calculate the molar mass of barium hydroxide. Well, before we do anything like we've been doing in the past, here's the formula of barium hydroxide. We first write it in ionic form. We know that barium has the symbol Ba, obviously, right? We know it is in group 2. So, and when it becomes ionic, it will be A+2 because it lost 2 electrons because it's a metal. The hydroxide, that is a polyatomic ion. Hopefully we know this formula by now. And it's OH, it's the base. Remember that chapter in acid-base reactions? That is the base. Well, we're going to put this formula together. You can see that I need 2 hydroxides to balance out the +2 of barium. Okay, therefore, our formula, we're going to need parentheses. Our formula is barium, Ba parentheses OH hydroxide and subscript 2. Okay. So let me clear that. So that's the formula we just went through. So again, when you're given a name, break it first into ions and then put them together properly with the right number of cations and anions. Now add up the mass for every atom. Okay. And so we have barium, you look that up. Barium has an atomic weight of 137.33. Oxygen, we have 2 oxygens, hence we got 2, and each oxygen has atomic weight of 16 grams. Okay. And then hydrogen is 1.01 for each one. There's 2 of them. When you do all the math there, 32, 16 times 2 is 32, and then we got 2.02, and we had the 137.33. You end up with a total of 171.35 grams per mole. That is the molar mass of barium hydroxide. So again, if I were to weigh out 171.35 grams of barium hydroxide in the lab, I go to the balance, weigh it out, I have 1 mole. And if I double that weight, guess what? I have 2 moles, right? And if I cut that weight, that mass by half, do I not have half a mole, right? And if I break that half even further, I get into quarter mole, so on and so forth. Right now, we got nice even whole numbers, but that's not always the case. But regardless, it's still going to be a mole, quarter mole, 0.25 moles, for example, so on and so forth. It is, again, like you can say, I say to you, All right, half a dozen eggs. Don't we all know, hopefully, that half a dozen represents six, right? Okay, quarter dozen. What's a quarter dozen represent? How many eggs do I have in a quarter dozen? Hopefully you come up with three, all right? And the same thing with three-quarter dozen, and so on and so forth. So it's the same analogy here. Similar, I should say. All right, Avogadro's number says that we have 6.0 through 6.02 times 10 to the 23rd anything. This is just a number per mole. Guess what? It's another ratio. Okay. And I can write that ratio either how it's written on the left or how it's written on the right, with atoms, molecules, bananas, oranges in the numerator and moles in the denominator, or inverted. Okay. And which one I use depends on the question that I'm being asked. So, for example, they're asking you here, how many calcium atoms are in 0.25 moles of calcium? All right, well, I'll tell you what, don't need to think too much about it, because the best way to attack this problem is to write down what you're given. Okay, and so I'm given 0.25 moles of calcium. Okay, and obviously I'm going to have a conversion factor here. But then I look at my units that I'm looking for. I'm looking for atoms, unit-wise, with calcium. Okay, what does that mean? That means that I'm going to have atoms in the numerator, and obviously I need moles in the denominator. Okay, so I'm going to be using this conversion factor, where 6.02 times 10 to the 23rd atoms, in this case, per 1 mole. Notice that my moles cancel. I have atoms left over unit-wise. Now it's a matter of you doing the mathematics. And again, this is where your scientific notation and calculator comes into play. Type in 6.02. Remember, you either have, it depends, you have a button that looks like this, okay? Or a button that has a double EE, looks like that, or a button that has an EXP. Okay, one of those three buttons. So you type in the 6.02, and then you hit one of those three buttons that you have. Do not use the button that's all by itself that says 10 to the X. Okay, do not use that one. No, it's going to be a little X in front of the 10 to the X. And that is the scientific notation. Some of the newer calculators have that system. And so you type in 6.02, hit one of your three buttons, and then you type in the 23 to give you the exponent. And then you just do the math like you normally do, hit the multiply, enter 0.25, hit equal, and then you got your answer there. Okay? That's a refresher on your scientific notation on your calculator. And so you set that up, and you should come up with 1.51 times 10 to the 23rd. Now, Avogadro's number is a number, so it's not utilized with respect to sig figs. Remember, sig figs haven't disappeared. Sig figs are always being used. And so it's like saying, you know, it's an exact number, 1, 2. It's a big exact number, but it's an exact number. So it's not used to determine the number of sig figs. But 0.250 is, okay, that comes from originally from a measurement and transferred over. So you got 3 sig figs, so your answer should have at least 3 sig figs. 1.51 times 10 to the 23rd. That is quite a bit of atoms. That's a 0.25 is the decimal number for a quarter mole. That's a quarter mole of calcium has that many 1.51 times 10 to the 23rd. Okay. And look at your answers. Okay. Just think about this for a second. I mentioned this in your calculations way back when, that give your answer some thought, because if you look at this number here, 1.25, and you're multiplying, this represents a quarter in decimal format to help you out, right? And you're taking a quarter of 6. So your number, if your number ends up with that's greater than 6.02, then you did something wrong in the math. That number should be much less than 6.02, okay? And so just because your calculator types out a number, don't be quick to just give that number. Look at your number. Does that number make sense based on the mathematics that you're doing? All right. Second problem. Calculate the moles of 3.75 times 10 to the 27 molecules of oxygen gas. So now we have a number of molecules, and we're going to calculate that and put it into a mole. It's like saying, okay, I have 6 eggs. How many dozen does that represent? Okay. And obviously it's an easy number. It's half a dozen. And this is what was happening here. You got molecules and you're asking how many chemist dozen does that number represent? Okay. And like I stated, when you have these problems, just write down what you know, because that really helps you to determine what direction you need to go. Because sometimes you have a problem that just doesn't make sense. You're like, I don't know about this, but you do know that you are given this information. You also know that you're going to have some kind of conversion factor, and based on the problem, units have to end up with moles, okay, of O2, because that's what the question is. So obviously my conversion factor here, since I got molecules of O2, I need molecules down in the denominator here. And I need moles in the numerator because I want my molecules to cancel out. So it looks like that's the one I'm using, the one on the right. I'm inverting Avogadro's number. And so I'm taking 3.75 times 10 to 27 and dividing by Avogadro's number. And that should give me the number of moles. I'm going to set that up. And I should end up with 6,230 moles of oxygen. Okay. Okay. That MLCLS, that's shorthand for molecules. So don't let that confuse you here. This number here, that cancels out, that cancels out. That's shorthand for molecules. Okay. Moles in the numerator, which is what I'm looking for because the question asks for moles. And as I stated way back when, I said, if you set your problems up in this manner with conversion factors and you follow the units, you would not have a problem with making sure you set it up properly. You will set it up properly. And you'll get credit when you're asked to show a problem because you set it up properly. Now, 99% of the time, I can guarantee you 99% that if you set it up in the manner I've been talking about, it's set up properly. I can't guarantee the 1% because you're in control of the calculator. Okay, you're in control of pushing those buttons. All right. So that's the introduction to some of the calculations that we're going to be seeing, and not to forget it, because the mole concept is very important when we get into calculations. And I stated, to get from apples to oranges, I need to go through moles. That is our common factor between the two. Okay. All right. So here they're asking you, how many grams is 1.667 moles of oxygen gas? All right. A couple of things to remember here is one, they are talking about oxygen gas. Okay. If they would have said oxygen, then they're talking about the element all by itself, but they're said oxygen gas. So this is something for you to remember, in that oxygen gas is one of the diatomic compounds. Remember, there's 7 of them. Okay, just like they would say hydrogen gas versus hydrogen. Hydrogen would just by itself would imply just the hydrogen atom, one of them. Okay, so we're dealing with the oxygen gas. All right, so what does that mean? That means that I need to calculate the molar mass. I need the molar mass for oxygen gas. Well, each oxygen weighs 16 grams per mole, and there's two of them, so it's a total of 32, 0.00 grams per mole is the molar mass. I'm going to call it molar mass of oxygen. All right, so we write down what we're given. We got 1.667 moles of oxygen gas. Obviously, we have a conversion factor coming here. And what are we looking for unit-wise? We go back to the problem. It says grams of oxygen gas. All right, that means that grams is the numerator and moles is in the denominator, okay? And so grams is on top, that's 32 grams per 1 mole. Okay, check my units, okay? And now I simply multiply 1.67 times 1.667 times 32, and that gives me the number of grams of oxygen. So this is my breakdown of the problem, okay? And how you go at it, you just put down what you know, put down where you gotta go, and then use my conversion factors to get me to where you have to go with respect to units. Okay. You know what? Let me back it up then. Let's do the same thing here with the next one. Then I'll show you the answers. All right, let's do number 2. Says how many moles is 45 grams of silver? Oh, wrong one. 45 grams of silver. All right, well, we got to look silver up, and that is, its atomic weight is 107.87 grams per mole. Oh, now the thing about atomic weights, I know you'll be tempted to go on the internet and determine what it is. Don't do that. Use the atomic weights given to you in the periodic table. Oh, simply because, as I stated, the atomic weights are the averages of whole numbers, okay? And that means that the number, when you average, if you take it, for example, average the number between 4 and 5, you end up with a decimal number, 4.5, right? Okay, so what means that when you average out whole numbers, you get an infinite number of significant figures. And sometimes when you look things up, they're going to give you a whole bunch of numbers there, and you're going to use that, and it's going to throw you off in your numbers. Not saying that would be incorrect, but Canvas would not recognize it, because Canvas recognizes the answers based on the number of sig figs that you use on our periodic table. So use our periodic table to determine the atomic weights of the elements, okay? So that comes from the periodic table, 107.87 grams per mole. All right. So we are given 45 grams of silver. And, you know, I would definitely keep the units there so you know what's going on. And we need to get to moles of silver. So that being the case, that means that I'm going to need moles in the numerator and grams in the denominator, because my grams need to cancel. So that means that my atomic weight, my molar mass, goes, in this case, you'll hear the term atomic weight, and generally that means the atom all by itself. When we talk about the molar mass, we're talking about all the atoms in a compound, okay? Like we did water, it came up with a molar mass of 18. But atomic weight, normally we're just simply talking about the single element. So the atomic weight of silver was 107.87 for 1. My units look good. And so that means I take 45 and divide it by 107.87, and that will give me the number of moles of silver. Okay. All right. Number 3. They're asking you to how many grams is 0.554 moles of water. Obviously, here we need to know the formula of water, which hopefully you know is H2O. We went through the scenario of finding the molar mass, and that was 18.02 grams per mole, right? That was 1 oxygen at 16, 2 hydrogens at 101, 1.01 times 2. You end up with a molar mass of 18.02 grams per mole. Okay. So write down what we're given, which is 0.0554 moles of water, H2O. Obviously, we need a conversion factor here. And based on the problem, we need to get to grams of water. Okay. And so that means that obviously grams is in the numerator and moles is in the denominator. Again, that's one way to keep track of things. Things are going, you're going in the right direction. So the molar mass goes in here of 18.02 in 1 mole. Okay. Now you might be noticing a trend here that when you start with moles and I want to get to grams, I multiply by the molar mass. The other way around, if I start with grams and I want to get to moles, guess what? I am dividing by the molar mass. Let's say this is 100 grams per 1 mole. Notice that? So if I start in grams and I want in moles, I divide by the molar mass. If I start in moles and I want grams, I multiply by the molar mass. That's a little trend there that can help you out. But if you don't get that straight, don't worry about it. Go through this how we're doing it, keeping track of your units, and guarantee you set it up properly. Now the next step is you punching the numbers. All right, now here's a little bit different problem. It's just different in the sense that we're probably just going to have to add another unit. All right. Couple of things. What we're looking for, we want to know how many grams. Okay, that's what we're looking for. So way over here, we're going to have grams, specifically of potassium. Okay. Now we start off with 4.75 times 10 to the 16 atoms of potassium. Okay. And so we need a factor to get from atoms to moles. Remember our common factor when we're going from one point to the other is moles. And so we need Avogadro's number here, right? We need 6.02 times 10 to the 23rd, we call it atoms, okay, because we're dealing with atoms, per 1 mole of atoms. This is times 10. Okay. And so I need, based on the way I set up the problem here, what's going on? Based on the way I set up the problem, I need atoms in the denominator of potassium and moles on the numerator. Okay. And so I get 6.02 times 10 to the 23rd in the denominator and 1 mole of potassium. So this first factor gets me to moles of potassium. I need to, when I start with atoms or molecules and I need to get to moles of whatever I'm starting off with, I need to divide by Avogadro's number. Okay. Next thing is potassium. Potassium has a atomic weight of 39.10 grams per mole. So 39.10 grams of potassium per 1 mole of potassium. So I got another conversion factor right here that I need to get rid of moles. So guess what? Moles go to the numerator, right? Keeping track of my units. And 39.10 grams of potassium are in the denominator. So checking my units, everything cancels out. I end up with grams of potassium, which is what I'm looking for. So now you do the math. Divide 4.75 times 10 to the 16 divided by Avogadro's number, multiply that by 39.10, and that gives you how many grams of, let me clear my mess up. You can see the answer there. Oh, all right. So the first one requires you have 1.667 moles of oxygen, okay, gas. It has a mass of 53.34 grams of oxygen. Okay. Now, 45 grams of silver corresponds to 0.42 moles of silver. And then 0.0554 moles of water is almost 1 gram of water for 0.998 grams of water as 0.055 moles of water. And then this large number here, potassium, 4.75 times 10 to the 16. That is a lot of atoms. Think about it. Move that decimal point over 16 times from the right up to the 4. And yet, that large amount of atoms, once you go through the calculation, weighs 3.09 times 10 to the negative 6 grams. Most balances in the most balances in the lab that we would use couldn't weigh that amount, and they don't have the precision or the accuracy to measure that. But it definitely gives you an idea as to that small quantity of potassium, how many atoms exist there. Very, very large with respect to the number of atoms, which again, putting that in perspective gives you an idea of how small these atoms really are. Okay, now this is we get through example using, we did the molar mass for some few examples. We talked about the atomic weight of the elements and the molar mass of certain compounds, meaning one or more atoms in the molecule. Now, if you just figure out the formula like we've been doing, from there, let me go back to that. Like we did barium hydroxide, first write out the formula, the ions, put them together properly in the right ratio. Once we do that, add up the atomic weights for every atom that contributes to the compound, and that gives you the molar mass, regardless of how big it is. Even if you don't know what the molecule, you may be given a formula, which is humongous. You can just add them all up, and you get the molar mass for that compound. Okay. And then the atomic weights for the single elements. So atomic weights generally refer to the single element. Molar mass refers to the compound or molecules. Now, when we get to gases, and now here's the thing about this. This only applies to certain conditions, okay? And we call those conditions STP. STP represents 0 degrees Celsius and 1 atmosphere. Okay, 1 atmosphere. We are here approximately 1 atmosphere. If we start going up in the air, there's less mass up there, so there's less atmosphere. So there's not as much pressure on this. I'm gonna see if I get a calculation, but we can calculate that. There's a lot of mass out there. I mean, quite a bit. If we take a unit area 1 meter by 1 meter and go up maybe 10,000 meters. That's 10,000 cubic meters of mass that's hitting on you. And if you do a calculation of, say, it has a density of 1 meter, 1 kilogram per meter approximately, you have approximately 10,000 kilograms of mass smashing you. We don't feel it because in the opposite, for every action, there's an opposite reaction, if you will. So for the 10,000 kilograms of pressure that are put on us out here that could represent 1 atmosphere, there's 10,000 kilograms of pressure being exerted counter. So we're happy. We're okay. We don't blow up or clean chin. Okay. But if you go down to the ocean, a few thousand meters, now you got a lot more pressure and you will squish like an aluminum can because we don't have enough pressure to exert the counter pressure. But yet there are animals down there, the whole environment down there deep in the ocean that survive this and survive these deep pressures for the same reason that we survive up here, because that's how they're acclimated to handle those high pressures. And there's crabs down there and all kinds of animal life down there. Anyway, but for 1 atmosphere, which is approximately 1 atmosphere here, and at 0 degrees, 1 mole of gas, okay, of any gas, which is hydrogen gas, any gas at all, occupies a volume of 22.4 liters, okay, 22.4 liters. Let me go back to the slide. So that is called STP, standard temperature and pressure. So at STP, things like hydrogen gas, fluorine gas, ammonia, xenon, methane, they have 1 mole. There's 1 mole of that gas, okay? Well, all of them have in common Avogadro's number of molecules, 6.02 times 10 to the 23rd. But because they're different atoms, different amount of mass, different number of protons and neutrons and so forth, they're all going to have a different molar mass. Makes sense, right? Just like that example of 1 dozen small eggs, 1 dozen medium eggs, 1 dozen large eggs. Yeah, they all got 12 eggs, but they're all going to have different weights because they're all different sizes, okay? And so the hydrogen gas has a molar mass of 2.01 grams per mole. Why 2.0, 2.02? Because each one is 1.01. And it's a gas, hydrogen gas. They didn't say hydrogen atom, say hydrogen gas, and it's diatomic. Fluorine is also diatomic, and therefore its atomic molar mass is 38. Ammonia, you add up the nitrogen, you add up the hydrogens, you end up with 17.04 grams per mole. Xeon, you look up the atomic weight on the periodic table. It has an molar mass / atomic weight of 131.29 grams per mole. And methane, well, methane has 16.05 grams per mole molar mass. That's because it's got 1 carbon at 12, 4 hydrogens at 1.01 each one. Add them all up, you end up with 16.05. What they all have in common is a volume when they are at STP. Now, I can't overemphasize those conditions because it is not true when they are not at STP. So if a problem states that you are at STP, or they state you're at 0 degrees in 1 atmosphere, which is STP, then this relationship can be utilized, meaning that you got another ratio here, okay? Another ratio that says 22.4 liters of gas, there's 1 mole. I can write it like that, or I can write it with moles in the numerator, denominator, excuse me, vice versa. No different than the conversion factors we did or have been doing now, and the ones we did when we were converting from English to metric units and vice versa, okay? That is nothing more than another ratio, liters per mole or moles per liter. And which one you use depends on the question and what units you're looking for, like we've been doing. And only true when you're at STP. If there is no STP, I can't overemphasize this. If no STP is mentioned, and there's no mention 0 degrees in 1 atmosphere, then there's no answer, because that you can't calculate anything, because it's only at those conditions. All right, so now gases are mostly in space, so we know, but at that temperature and at that pressure, they occupy a volume of 22.4 liters for any gas at STP, any gas. Okay. So here's the ratios that we can set up, either liters in the denominator or liters in the numerator. And we go about the problems no different than we have been before, okay? And we analyze the problem, right? Break it down. It says, what is the volume? So those are the units we're looking for. What is the volume? And normally, you know, because we're using these conversion factors, the volume here is in liters, okay? It's understood to be in liters. They may ask you to do milliliters or some other volume, but that's okay. You got to get to liters first, and then from there you can convert to whatever volume you want, units you need, but you got to get to liters. Okay, so what is the volume of 1.25 moles of argon? So we're given 1.25 moles of argon, okay? We know we need a conversion factor here, right? We know we need liters as the final answer. So it's liters up here, moles in the denominator, okay? And more importantly, we are at STP. Okay, that means that we can utilize a 22.4 liter per 1 mole relationship because we are at STP. And so now check your units. Units cancel, leaving us with liters with respect to units, which means we're good to go. You do the math. Okay. All right, let's do another one before I show the answers here. Another one says we're talking about oxygen. Okay, no different. Again, it's a gas, and again, we're at STP. Okay, and this time they're asking us how many moles. So our units end up in moles of oxygen. Okay, we are given 30.4 liters of oxygen. So we have a conversion factor here. We want moles in the numerator and liters in the denominator, because we want the liters to cancel, moles. So we got 22.4 on the denominator and 1 in the numerator. Because we are at STP, we can utilize that relationship. Okay. Check my units, liters cancel, moles are there, we're good to go. Okay. A little bit of a different problem, but that's okay, no problem, we'll break it down. Asking you here, what is the mass? Well, the mass, 99.9% of the time, we are talking about units of grams, okay, of chlorine. We know that chlorine, let's say chlorine gas, so that is Cl2. Chlorine gas is 35.2, 35.4, what is it, 3 or 5, sorry. We need 2 of them, that's 10, that's 9, 10, 70.90 grams per mole is my molar mass. Use my little mess there. It's 35.45 times 2 because there's 2 of them, right? We want the mass. So we're given 4.50 liters of chlorine gas. So we need, and we are at STP. So we can use that relationship, 1 mole equal to 22.4 liters. So liters obviously is in the denominator because we want to get rid of liters, and we need to get to moles because there's no way to get from liters to grams without going through moles. Okay, so we got to get the liters out and do the moles. So now that's 22.4 liters in 1 mole. So my liters cancel, okay, leaving me with moles, but it's not in gram. I need one more factor, and that would be with moles in the bottom and grams on top, and that would be my atomic weight, my molar mass, which is 70.9 grams per 1 mole. So moles cancel, leaving me with 70.9 grams per chlorine. So my units are set up properly. Now it's a matter of you doing the math. Well, let me clear the mess here and bring them up. Here's the first one we just did. We went through. Okay, moles cancel, leaving us with liters of gases because that's what that question asked for. You want to know the volume. Second one, similar situation, but we inverted the 22.4 liter per mole. Okay, because we wanted units of moles. Okay, and then finally the last one, we used 2 factors here because it got us from went from liters, got that converted to moles, and then from there, using the molar mass, it got us to grams. So you see how it looks like we got liters, we got apples way over here, and we got to get to grams, oranges over here. Well, we can't do that without first having to go through moles, because that is our common factor to get from point A to point B, moles. And this is going to be true for all reactions. This summarizes everything for you, okay, with respect to mole calculations. And there's another one we're going to be doing that does even more summation, but right now, here's the first one. Okay. The ultimate goal is to get from grams to, let me change the color here. The ultimate goal, for example, would be to go from grams to liters and volumes. Well, we can't go directly. We first have to go through moles, then down to liters, okay? The ultimate goal is to go from grams to atoms or ions or molecules or whatever the case may be. Well, we can't do that directly because we got to go through moles to get there. Okay. Now I'm shooting this arrow in one direction, but remember, these are in both directions. So I can start with, let me change the color here. Let's go blue. I can start with atoms and go to volume, but I have to go through moles. Or I can start with volume and go back to atoms. Or, let me clear it because it's getting kind of messy. I can go this direction, both directions, okay? Or I can go that direction, but in both directions. And obviously I can go from here to here in both directions, okay? It's not a one-way street. Not a one-way street. But the important aspect is I can't do any of this without going through moles, okay? Moles is our common factor. And it's going to be true with respect to our reactions where we talk about if I start with 10 grams of carbon, how many grams of oxygen do I need for a reaction? Well, I can't go directly, but I can first convert the grams of carbon to moles, find a relationship between moles of carbon and moles of oxygen, which gives me now the moles of oxygen. And then with the atomic weight or molar mass of the oxygen, I can get the grams of oxygen, okay? And that's the important part. Doc is that kind of the moles, excuse me. Moles, that is crucial. We gotta get through those. Through moles, we gotta calculate. In this case, you can see grams to moles, we need the molar mass. Moles to atoms for anything, we need Avogadro's number. And only if we are at STP, I can't emphasize that, then we can use this relationship. Okay, and that's how we get from point A to point B. If STP conditions are not met, then that calculation is, we couldn't do it. For example, how many grams does 17.35 liters of neon gas mass at STP? All right. So they're asking you, let's break it down. How many grams? We're talking about neon. This is neon gas. Yeah. So we want to know eventually. Let me change the color here. Bring it out a little better. The yellow better. Yeah. We want to know how many grams of neon gas do we have? That is what we're being asked to calculate, the ultimate goal. I write it down because that helps me keep track of where I need to be and I don't get lost with direction. If I'm given 17.35 liters, I can write that down, 7.35 liters of neon gas, okay? And the other part of the problem is STP, which means that I can use the 22.4 liters is equal to 1 mole relationship, okay, of any gas, because we are talking about neon gas. All right. So, but since we are STP, they're telling us we want grams. So what is it? We can put the first conversion factor, 22.4 liters of neon, because liters cancel, to give me 1 mole of neon. Okay, leaving me mole of neons, and my liters cancel. That takes care of the liters, but it leaves me in moles. Well, I can't. I need one more factor, do I not? Because the question asked me for grams. So I need the atomic weight of neon, which, sorry, I got 20.8 grams per mole for neon. Okay. I want grams in the numerator, moles in the denominator. Why? Because I want my moles to cancel and leaving me with grams, because that's what the question asked for. So I plug in my 20.18 and 1 mole. Okay. Now I take 17.35 divided by 22.4, multiply that by 20.18. That should give me the grams. Okay. Let's see. Okay. So here we go. First factor, you can see that, converts it to moles. Then the second factor converts it to grams. So I need 2 factors in this particular reaction. The second part says, how many atoms do I have here? Well, dealing with how many atoms tells me I need Avogadro's number. Right? So for atoms, I'm going to need 6.02 times 10 to the 23rd, in this case, atoms, equal 1 mole of atoms. That's my conversion factor. Okay. And I'm still given 17.35. So it looks like everything here is the same for the first part, because I got to get 2 moles. Okay. Where we differ is the second conversion factor, because now I want number of atoms. So I got 1 mole on the bottom. So this Avogadro's number is written with 6.02 times 10 to the 23rd atoms per 1 mole. So moles cancel. Okay, my liters cancel, leaving me with atoms, and now it's a matter of you plugging in the numbers. Okay, so we plug it in. That's what we're looking for. Here we go. Okay, and so you can see that in two different units. Here we got grams, here we got atoms. But for STP conditions, we eventually were able to use the 22.4 liter per mole relationship because that put us with moles, which is what we need to get from point A to point B. Okay, we got to go through moles. Oh. Okay. All right. I'm getting pretty close to the end of this chapter too. Density, we're back. I think we did talk about density, where density was a ratio. Again, yeah, we did way back when. It's a ratio of mass over volume. Okay. Now, at STP, you can calculate the density of a gas without having to do any actual measurements. Because what do we know about any gas? Well, first of all, we know the formula. We will be given the formula. With the formula, we can calculate the molar mass. Okay. Also, we know that at STP, any gas has a volume of 22.4 liters. Okay, so we can essentially take the molar mass of ammonia, which is 1 nitrogen, 3 hydrogens, gives us 17.04, and divide it by the molar volume, because we're at STP, which is 22.4 liters per mole. Okay, and we end up with the density. Now, think about this for a second with respect to just the units. Why is that possible? Okay, if I look at the units, I'm going to write it grams per mole, and I'm dividing by liters per mole. Okay, so I'm taking a fraction and dividing by a fraction. What do? I invert the denominator, which is the fraction, and then multiply. And so that becomes grams per mole becomes, I invert the liters per mole, and it becomes moles per liter when I invert the denominator and multiply it out. Guess what? Moles cancel out, giving me the units of grams per liter. Okay, which is density, which is mass over volume. So for gases at STP, you can use this relationship. All right, percent composition, pretty close to the end here. I'm gonna, if you bear with me, we can just knock it out. All right, now we talked about the molar mass, okay, and how to calculate that. All right, now we take it one step further. We can determine the percent composition of every element in the compound, okay? And how do we do that? Well, take, for example, water. We know that the total molar mass of water, which we calculated to be 16 for hydrogen and 2.02 for the both hydrogens, is 18.02. Okay. So that is 18.02 is the total molar mass for water. Then we know there's the only elements involved with this is hydrogen and oxygen. So we take the contribution of the hydrogen, which is 2.02, divided by the total molar mass times 100. Guess what? We end up with water having 11.2% hydrogen. We can do the same thing for the oxygen. We know there's one oxygen at 16.00 divided by the total molar mass of the molecule, which is 18.02 times 100. And that tells us that oxygen contributes 88.79% oxygen. And that is true for water, whether you find it here or you find it in China or whether you find it outer space. It has that contribution, that percent composition, okay? Note that the percent composition should all add up to be 100%. So 11.2 and 88.7 should be approximately 100%. You might be off maybe 0.01% or so, but it should all total up to 100%. We use that percentage to back calculate to figure out the formula. We do this in the real chemical world. You know, we make a new compound, we send it off for analysis, determine how much carbon, hydrogen, sulfur, whatever we want. Numbers come back, we back calculate to come up, figure out how many carbons and how many hydrogens we have. And then we use that with information, what we call spectroscopic information to verify our structure. That's how we know that this structure is so-and-so, or it looks like this, because we have spectroscopic data and all kinds of other data to verify that structure. All right, so that is percent composition. So let's do this one last slide and we'll be done. Here we have find the percent composition for TNT. Okay, you might know what TNT is. It's, you know, AKA dynamite, but its true name is trinitrotoluene, hence TNT. Its formula is given up in the top right corner. There are 7 carbons, there are 5 hydrogens, and there are 2 NO2 group, 3, excuse me. So that ends up with 3 nitrogens and 6 oxygens. Okay. Now to calculate the percent composition, we first figure out the total molar mass, always using the Chem 130 atomic weight. Okay. Carbon is 12.01. There's 7 of them. Okay. So that's a total of 84.07 grams per mole for the carbon. Hydrogen, there's 5 at 1.01 for each one. That's a total of 5.05. Nitrogen, there's 3, 14.01 for every 1 nitrogen. That's a total of 42.03. And then oxygen, there's 6 of them with atomic weight of 16.00. So that's 96 grams per mole for the oxygen. Tally all that up. The molar mass, the total molar mass for TNT, okay, trinitrotoluene, aka dynamite, is 227.15. Yes. Okay. Give me 3 minutes and we're in with the chapter. The chapter is done. So I know the time's almost up. 227.15 grams total. Now you go back and you do the division for each component, each atom. Carbon's 84.07, each one. And guess what? Carbon consists of 37.01%, hydrogen's 2.22, nitrogen's 18.5%, and oxygen is 42.26%. That is the percent composition of all the elements, and that is what TNT is made up of. Okay. All right. Try these at home. You have here's a question: how many liters will 3.425 grams of carbon dioxide occupied STP? You should end up with 1.74. How many molecules in 3.425 grams of carbon dioxide? You should end up with 4.65 times 10 to the 22 molecules. And then finally, how many grams? 3.0 times 10 to the 15. Okay. Carbon dioxide, you should end up with 2.2 times 10 to the -7 grams. Try those at home, see if you can get those answers, set it up properly, use the process that we just went through. And if there is a problem, come Tuesday or send me an email, we'll go through it. Okay. So those are typical types of questions that could be asked. All right, ladies and gentlemen, congratulations. You are done with chapter 12. Let me stop the share and